we are meeting in the group of soil moisture monitoring of the harmonious construction. Today, the aim of the activities to identify the main achievements of working group 3 gained so far, and try to identify potential path for future research activities. I give the floor to Yixin Zheng, who's being the leader of this working group that has been one of the most fruitful working group in harmonious construction. So, Yixin.
Okay, thanks a lot, Salvatore. First of all, I'm sorry I cannot be in this site together with you guys due to other complications. But I'm really honored, Salvatore. You say this is the most fruitful working group of Harmonies. Well, this is mainly also partially due to the fact, let's say, there's iAqueduct project. Let's say originated from the ideas of working group 3, and then we take there further to do some science links to soil moisture topics. Before I introduce the talk, maybe I briefly, well, there's a lot of I will briefly show my window in terms of the where it is showing window or in your entire screen. Can you see my screen? Yeah. So I will briefly just say, okay, this is the agenda for this afternoon. So this is not, let's say, kind of a summary, I would say, for working group 3 activities, but actually yesterday there's a presentation, and from there we know there are some papers published from working group 3 activities. And today, of course, some of them are also already accomplished papers, but also it is kind of, how to say, it's a kind of an introduction to that topic, but it's trying to lead to further collaborations. So I fully agree with Salvatore. We should keep the presentation concise within the time, and then we'll leave a little bit more time for discussion for further activities. So without further ado, please, Nicholas, are you able to share your screen?
Yes. Okay. Hi, everybody. My name is Rick.
It seems your screen is gone, Nicholas.
If I talk now, do you hear me? Yes, totally.
I think it's okay. Because we need...
I have to mute myself in here.
And now?
Now.
Perfect.
Okay. Yes. Okay. 1 second. Now we're okay.
Hi everybody, my name is Nicolas Francos. I am a PhD student at the University under the supervision of Dr. Riel Vendor. The name of this presentation is a transfer function to predict soil surface reflectance from laboratory soil spectral libraries. Today, I will not talk about the first paper, that was the previous part of the study of the transfer function, because I presented this.
To mute the speakers. Just the echo is coming from the.
I have to mute the presentation. 1 second.
Yes. It's not.
Now?
Okay. Perfect.
Excellent. So I just will focus on the second part, that is this paper of the transfer function. The purpose of the Ayacucho project is to reduce the gap between satellite observations and local needs for a better management of water resources. Nowadays, there are several initiatives to create soil spectral libraries because these datasets have a high potential to be used to predict soil attributes. A short definition for soil spectral libraries is that they are large datasets that contain spectral measurements and chemical measurements. And the problem of these datasets is that as they are created using these target soil samples, it is not clear if they can be used to infer the field condition, because in the field the soil surface is undisturbed, and the undisturbed soil samples represents the remote sensing view from the sky. So it is important to reduce this gap in order to represent correctly the aerial view. So in this study, we focused on the water infiltration rate because it's a soil surface dependent property. This is because with the raindrops energy, when the drops fall into the soil surface, the particles jump up, and then those particles that are heavier falls, and then those that are thinner. This process is repetitive and is cumulative and seals the soil. Here we have an example of one sample that was collected to the laboratory. Here we can see in the ratio, the red spectrum, what quantitative spectral properties we can lose after the sampling procedures, between them iron oxides, organic matter, hygroscopic water, and clay minerals. In order to create our dataset, we used the Soil Pro assembly, that is a closed chamber with its own illumination source and a constant geometry, in which at 45 degrees there is an aperture in which the optic fiber of the spectrometer is connected. So it is possible to acquire spectral measurements in the field under laboratory conditions without atmospheric illumination. For this study, we acquired field spectral measurements, laboratory spectral measurements, and also water infiltration rate measurements that were done in the field. Here you can see spectral measurements with the soil assembly connected to the ASD spectrometer in the field. The mini disk infiltrometer, that was the instrumentation to measure the water infiltration rate. The places from where we collected the samples in 3 countries across the Mediterranean basin: Israel, Greece, and Italy, from 6 different fields. The central location of the fields from which we collected the samples, and I will summarize here the methodology. The idea here was to predict the field reflectance using as input the laboratory measurements. For this end, we used as input the whole spectrum of the laboratory, and we predicted separately each band of the laboratory level to then merge all the predictions of the field level. For this end, we used 2 groups, one for calibration and the other for validation. 90% of the samples for calibration, the other 10% for validation. And then once we predicted the field spectrum, all these predictions were smoothed using the Savitsky-Golay method. To check the spectral similarity, we evaluated 2 indicators. One of them is the spectral angle mapper, and the other is the ASDS, the average sum of deviations squared. The spectral angle mapper focuses more on the spectral features, regardless the albedo effect. On the other hand, the AFDS focused more on the albedo effect that in general represents the general values of all the bands and not in the spectral features. So there are two indicators that evaluate different aspects of the spectrum. This chart represents the distributions of the values. The blue chart represents the field against the transfer function relationship, and the red distribution represents the field against the laboratory relationship. And as the blue distribution in both indicators tends to be to the left, this is a good indication of a good correction. Here we have 6 samples, and we obtained similar distributions, similar spectral signatures, between the field and the transfer function. The blue spectral signature is similar to the black one, and the red that represents the laboratory is very different from the others. And this is the root mean squared error per wavelength, where along all the spectrum, the field against the transfer function relationship presented lower values. So then the idea was to predict the water infiltration rate in the different scenarios: the field, the transfer function, and the laboratory. The best results were obtained in the field, then the transfer function, and finally in the laboratory, indicating that there is an improvement in the predictions of the water infiltration rate. That is a soil surface dependent property. That is, if we have time, I can present results from another study. If not, we can continue. Jan? Jan?
Yes, yes.
No, I said that I finished with the transfer function, and if we have time, I can continue with another study.
Maybe, yeah, looking at the time, maybe we can, how many slides you have further? Yes, if it's only few, then you can go ahead, but if it is another 15 minutes, then maybe we can take it.
Okay.
Maybe you can have a quick going through.
Okay, so here in the upper right chart, we have the Planck curves of a black body with different temperatures, and in the lower right figure, we have the radiant spectrum of the Earth and the Planck curve of a black body with the same temperature of the Earth. Then, by dividing the temperature of the black body that have the same temperature of a given object against the radiance of the object in question, we can extract the emissivity, and this is the information that we use for further analysis in the thermal spectral range. Here you can see a teleopsic spectral camera that measures the emissivity spectrum between the 8 to the 12 microns spectral range, ground measurements. So in the thermal emissivity spectral range, we can obtain well-defined spectral features of the quartz, the clay minerals, and also the carbonates. And recently, Notesco generated indicators to estimate the quartz to clay minerals ratio just using a specific wavelengths in the thermal spectral range. So in this study, we aimed to use the optical spectral range to predict this indicator and also to predict the chemical relationship between the quartz and the clay minerals, taking advantage from the relationship between the optical and the thermal spectral range. As we can see on the right, there is a strong relationship between the index developed from the thermal spectral range and the Series aluminum ratio that represents the relationship between the quartz and the clay minerals.
Only
Aluminum,
one outlier. There is only one outlier in the
yes, but this is the other study.
Ah, okay.
I just present that to illustrate the relationship. Yes, there's one outlier, but the relationship is very strong. Aluminum represents the clay minerals and steel is the quartz. And this relationship is also indicative for the soil texture because there is a strong relationship between the sand and the quartz, and aluminum as clay minerals, the clay content. So in the upper left chart, we can see well-defined spectral features of the quartz, the clay minerals. In the lower chart, we can see the classical spectral feature of the clay minerals at 2,200 nanometers. And in the right chart, we can see that the quartz have not marked spectral fingerprints. So it's not it's a problematic soil attribute to predict using the optical range. This is the flowchart of the study. So as I explained previously, the idea is to check the possibility to predict the quartz and also the quartz to clay minerals relationship indirectly using the optical spectral range. And for this study, we evaluated four different attributes: the quartz, the clay minerals content, the SQCMI, that is the index developed from the thermal spectrum range, and also the quartz to clay minerals relative abundance, but measured chemically. This correlation matrix was created to examine indirect relationships from other soil attributes that can be assigned to the spectral features, to the future importance product of the spectral-based models. Thus, it's possible to find reasonable explanations. For example, the specific surface area, that is a texture indicator, calcium carbonate that have marked spectral fingerprints in the optical range, kaolinite, elite, and smectite are clay minerals, and hygroscopic moisture that can also be related to the clay content. So, firstly, with the quartz, it was not possible to obtain a good model. Then, as we found in the future importance product that between 2,000 and 2,500 nanometers, they are the most marked spectral fingerprints, but also are related to the clay minerals, we decided to create a new model, but using just this spectral range. And again, the quartz was problematic in this spectral range, in the optical. Then with clay minerals was possible to obtain a good model, R²70. Then, if we predict the SQCMI, that is the index generated from the thermal spectral range, it was possible to predict generate a good model, also using the whole optical range and also just focusing on the 2,000 to 2,500 nanometers spectral range. And this is important because this is an atmospheric window and indicates a good potential to predict this relationship from aerial sensors. Again, this is taking advantage from the clay minerals and the hygroscopic water filters, as shown in the first model. Then, I cannot see here the lower part, but here we can see carbonates and also the shoulder of the water absorption at 2,800 nanometers. Then the quartz to clay minerals ratio also presents a high accuracy, but the SQCMI index presented a higher accuracy than the chemical measurements. So by taking advantage from the spectral emissivity, it's possible to obtain better predictions. This paper was published last year, and that is. Thank you.
Thanks a lot. Are there any questions in the room? If not, actually, I had one quick question. Maybe, Nicholas, did you try to use the approach to predict soil organic content as well?
Not in this study.
But you do try a similar approach, or using hyperspectral measurement, but also thermal?
No, still I didn't try to predict the organic matter using thermal emissivity, but there are studies that did that.
Okay. Thanks a lot. Then thank you, Nicholas.
Okay, thank you.
Then let's move to the next one. But Laszlo said he preferred to have a later talk, right?
Yeah.
We need to wait for your colleagues. Yeah. So in that case, maybe Li Jie, Qian Qian, I don't know who will present. Please, one of you share the screen. So Li Jie, you will talk, or I cannot hear you? Because I see Qian Qian didn't unmute yourself, so.
Okay, now I stop sharing the presentation.
Okay, thanks, Nicholas. Li Jie, can you share the screen?
Yes, I can.
Yeah. Oh, you should put your names as the first author, but go ahead.
Okay, thanks everyone. And the presentation topic is about an example of optimized machine learning algorithms to predict the soil moisture at a global scale. So the background is that the soil moisture plays a fundamental role in the water and heat exchanges between the land and the atmosphere. And at the same time, the machine learning and the deep learning methods provide possibilities to facilitate the understandings of the relationships between the available in situ surface soil moisture and some land surface features or atmospheric features at a global scales. So the purpose of this virtual mobility work is to provide a systematic comparative analysis of the advantages and the disadvantages of different machine learning and the deep learning methods, and to propose methodologies for building suitable predictors together with the ensemble models of optimized machine learning algorithms for soil moisture estimation. So this is the conceptual frameworks. We do the data collections and do the pre-processings from the in situ surface soil moisture and the predictors from satellite and reanalyze this data. Then we do the data splittings into the training data set, test data set, and the evaluation data set. Then we choose 5 to 7 different machine learning algorithms, and after doing the hyperparameter turnings to compare the performance of the different models. So this is the data we used for this work. We have the evapotranspirations, precipitations, and also antecedent precipitation index, which is weighted summation of the daily precipitation amounts with a spatial resolution of 0.25 degrees from area 5. And we have the vegetation index, including the NDVI, normalized different vegetation index, and the EVI, the enhanced vegetation index, which is from the MODIS product and MODIS 13A1 with a spatial resolution of 50 meters of daily data. And we also have the land surface temperatures and the daily land surface temperature differences between the day and night with the 2 meters air temperatures. But here the air temperatures is from the ERA 5 and the land surface temperatures from the MODIS product. Then we also have the soil textures, including the proportion of clay, sand, and silt. We have the porosities and the organic matter content. And all this data are from the soil grades with 250 meters spatial resolution. And this data is static. Then we also include the geographic coordinates informations, which means longitude and latitude of the site. Then last, we plus the elevations and also the topographic index. And the data has 90 meters spatial resolutions, and it's from the Merit Hydro. So this is the data set. The figure 2A is the distribution of the international soil moisture network sites over the Köppen climate classifications. And B and C is just a preview of the annual presentations and the NDVI. This is the data explorations. We compare the correlation coefficient between the different predictors. From these figures, we can say, I'm not sure if you can see my cursor. The soil moisture have the highest correlations with the antecedent precipitation index here. This is the data processing workflows. The first step is we collect the data and prepare it to harmonize the data at the daily spatial solutions. Then we split the data. 10% of the data are called independent stations. Those stats from those stations are not incorporated in the model trainings. Then the rest, 90% of the data were separated two parts. One is the training testing set with the 70% of the data from this 90%. Okay, and the other 30% is used for evaluate the models. Then we train the model with 70% of the data from the training testing set, and use the last 25% to test the models. Then using those evaluation set and these independent stations to evaluate the model performance. Then we compare the different model performance at the third step. So here we choose the 4 machine learning algorithms, including the support vector regressors, the random forest regressors, the k-neighbors regressors, and the ADA boost. We have more algorithms are still under processing. Maybe we update it later. Here, we're also using the hyperparameter turnings, which means to control the learning processes of the machine learning models, and to search the best parameter values in order to optimize the training procedures and achieve the maximum performance of the models. In this study, we're using both the Python packages, Grid Search CV for the hyperparameter turnings. So these are the parameters to be optimized in different models. I will not give details here. Then we have some preliminary results already. This is the result from the support vector regressors. Because the computational requirements for training support vector regressors on big data are very high, and if the samples are more than 10,000, it becomes very difficult. So we're only choosing the linear support vector regressors here. But the model trains very fast, but the model have some overfitting issues here. We can see the root mean square error for the soil moisture is pretty high, 0.16 cubic meters per cubic meters. And also the Pearson correlation is very low, it's only 0.32. Figure 6 is evaluation of the support vector regression models with some independent stations. We could say support vector regressors with the linear call is not suitable at this result. Then we have the preliminary result from the random forest regressors. Random forest model is an ensemble learning method, follows the bootstrap algorithm, with also aka Bayesian, that outputs a result based on many individual training models, or let's say trees. Here, the random forest regressors have a pretty better result. We have the root mean square error of 0.04 cubic meter per cubic meter for the test result. And from the evaluation, the result is also good. As we can see, the root mean square error mean is around 0.6 or 7. This is the result from the k-neighbors regressors. This regression based on the key nearest neighbors. The target is to predict by local interpolations of the targets associated of the nearest neighbors in the training set. So we also have a very good result with the root mean square error of 0.04. and like the Pearson correlation is 0.94. It's a very good result. This is a preliminary result from the ADA-boosted regressors. Again, the ADA-boosted regressors begins the regressions by fitting a regressor on the original data set, and then to fit the additional copies of the regressors on the same data set. But the result shown here is not very good, with the root mean square error of 0.1 in the test set. So we have a summary of these 4 models here. As we can see, at this moment, the random forest regressors and the k-neighbors regressors have a better performance. And also, we have the running times here for the preliminary results that maybe random forest performs a little bit faster. So the challenge encoded here is first, it's a long training times, because in this study we use more than 350,000 samples with 17 predictors for training the different machine learning models. So the training times can be reduced maybe after optimized the hyperparameters and reducing the number of predictors. And the second is the increased complexities of the parameter optimized tasks. The selection of the parameters for each machine learning and deep learning models weights and bias to the model performances, and makes it complex and requires expertise in model training. Last is the outlook. This study will provide the future importance of the same predictors in the different machine learning or deep learning algorithms, and the corresponding performance in terms of the training speed, the accuracies, and the robustness. The last is the optimized machine learning and deep learning algorithms can serve as a benchmark for producing the global scale sophisticated products in the future. So this is the presentation. Thanks for your attention, and all questions are welcomed.
Thanks a lot, Lydia. There is already quite some work there. Are there any questions online in the room?
I have a question.
Yeah.
Giuseppe.
Hey, Giuseppe.
Ciao. I'm wondering if you are planning to make also a validation of this big, huge model with the measurements at the surface.
Yes.
Maybe I skip the didn't pay attention.
At this moment, we have 3 kind of validations for the model. First is this training set. I'm not sure if you can see my cursor.
Yeah.
Yeah, this training set, but actually it's just a random synchronous data. And also we have this evaluation set, which is from the different years, but from the same stations. In the meanwhile, we also have some independent stations, which is not incorporated in the whole model trainings.
Okay, thank you.
Yes.
Okay. Further questions? Or otherwise, maybe one quick question from me. So, Zijie Qianqian, I mean, if you look at the performance of SVR and the ADA-Boost, yeah, I mean, I can do better job in Excel sheet, for example. So why SVR and ADA-Boost are performing, I mean, yeah, very bad here?
I can answer the first part. Why the support vector regressors is not good. Still, it's because the training times. If we're using some other cores, maybe the model performs good. But here we have too much of the training data, so we could only using the linear cores. But the linear support vector regressors will provide a very bad performances. And for the ADA-Boost is done by my colleague Duan Ting. So maybe if she's here, she can help me to answer the result.
Is Duan Ting here?
Yeah, I'm here.
Okay.
I can give some explanations about the ADA-Boost. Lijie, can you move to that slide? Yeah, since the AdaBoost regressor has a strong reliance on the base estimator, and the default settings estimator is decision tree regressor. So I think the poor performance has some result because of this regressor base estimator. So I think maybe we choose some other kind of estimators can change the performance. That's my idea.
Okay.
Yeah.
Thanks a lot. Yeah. Okay. Are there any other questions? If not, thanks a lot, Lijie, Duncan. Then we can move to next talk. So Lazaro, you still want to wait a bit?
Yeah, thank you.
Okay. Then maybe Dangyang, you can share your screen.
Okay. Can you see that? Can you see my screen?
Yes, please.
Okay. Dear sir and madam, good afternoon. My name is Danyang Yu, and I'd like to introduce my research. The topic of my presentation today is improving sugarcane growth simulation by integrating multi-source observations into a crop model. And I'd like to introduce you about my research from 5 perspectives: the background, the experiment, the methods, the results, and the conclusion. As we all know, the model can simulate the natural laws, and the agrohydrological model can simulate the interactions between the crop growth and the soil water movement. However, owing to the model simplification and insufficient information, agrohydrological models often have multiple sources of uncertainties. To reduce these uncertainties, the researchers often use the multi-source use the observations to constrain the simulations, and with the development of the technology, we can collect a multi-source data such as the underground data, the field data, the data, the UAV data, and the satellite data. This new monitoring method provides new guidance for agricultural development, but also cause problems such as a big amount of data and scale mismatch. So the issue how to understand the value of multi-source data for crop growth estimation and how to incorporate their information into a model is getting more and more attention. So most of studies use data assimilation method to investigate the data fusion problems. However, among the studies, the LAI and soil moisture are regarded as 2 significant variables to characterize crop growth process. However, the data fusion work has encountered several challenges. For example, limited by the model structure, new observations cannot be incorporated. And second, the root zone soil moisture is difficult to be observed. Then the water stress level is not equivalent to crop stress level. For sugarcane, we know plant height data is very easily collected by the UAV and is a direct index of the sugarcane yield. So we want to know whether we can use the information of plant height to better characterize the sugarcane growth. So the difficulties is that a reliable plant height growth model is still lacking, and also we should assess the value of plant height for yield estimation. To investigate this issue, we have conducted an experiment in Chongzhou, Guangxi province in China, and the period of the experiment is from 2016 to 2018. And we collected the meteorology data, the UAV remote sensing data, LAI, soil water, plant height, soil texture in 104 plots, as you can see here. And firstly, we constructed a plant height simulation framework, and we coupled a plant height growth model with the SWAP model, and then we use the RES data assimilation method to combine the information of the plant height simulations and the observations. Then we constructed the 8 data fusion strategies to investigate the value of LAI pH, the soil moisture, as well as the combination of so firstly, we has conducted a data worth analysis, and we can see the correlation coefficient between the yield and the plant height is the highest is around 0.775, which is much larger than that with LAI and that with soil moisture. So we can see the plant height is a very significant, important variables for sugarcane growth. And then we just incorporate these variables into the model, and the black line is the data simulation results. And as we can see, the data fusion method improves the simulation of LAI, the plant height, and the dry matter, and the soil moisture very significantly. After that, we compared the data fusion results with different strategies. Firstly, you can see Fig C and Fig D. We find that the fusion of soil moisture is less helpful to simulations because there are sufficient rainfall in Guangxi, which the precipitation is over 1,300 mm. So in Fig A and Fig C, we could conclude that compared with the traditional fusion of LAI and soil moisture, the fusion of LAI and plant height could achieve better yield estimations. So to investigate why PL performs better, we divided the sugarcane into 2 groups. The high yield group indicates the slight stress level, and the low yield group indicates a strong stress level. Then we compare the data fusion results in that 2 groups. As you can see, when we incorporate the LAI into a group, the LFS strategy performs worse in the slight stress level, but performs better in a strong stress level. This is because the canopy, the LAI, the canopy cover is saturated in that group, and the LAI cannot clearly reflect the difference of the different plots. But in strong stress level, the LAI could obviously to reflect the growth, the difference of sugarcane in different plots. In contrast, we find that the PFS performs worse in the strong stress level, but performs great in the slight stress level. This is because in the strong stress level, we could find the number of stalks arose significantly in that group, which reducing the value of the plant height. we can conclude it from this figure that the information of LAI and the plant height are complementary. So we could found that when we use the fusion of LAI and pH, it can perform good, whether in slight stress group or strong stress group. Now, regarding the soil moisture, we can see the value of soil moisture decline on the strong stress level because this group is also affected by other stresses such as the nutrient or disease or something others. Then we also investigate the effects of the development stages. We found that, of course, when we fuse all data in whole period into a model, we could get the great results. And the data in elongation stage also show its usefulness. But the value of the data deteriorate in mature stage because owing to the leaf synthesis and lodging. So we could so three main conclusions can be drawn here. Firstly, we could say plant height and LAI observations could both reflect the collective crop response to stress. The former reflects the height characteristics of the crops, while LAI reflects the density characteristics of the crops. Second, we suggest the fusion strategy of LAI and pH data as an alternative to traditional LAI and soil moisture fusion strategies to achieve the better simulation results for sugarcane. And thirdly, the observations during the irrigation period provide the most useful information for yield estimation. Finally, if you want to see a lot more details about our work, maybe you can see the paper which is published in the European Journal of Agronomy. Okay, thank you.
Okay, thanks a lot, Danyang. Very interesting work. Are there any questions in the room and online? By the way, I also copied the comment Brigitte, Qianqiang, and Li Jie typing in the chat for later reference. If there's no other questions, I will quickly ask Danyang one question. So as I noticed, when you incorporate the plant height and LAI, the performance or estimation is improved. But then if you further incorporate the soil moisture information, then the performance decreases. So I mean, for data simulation, usually if you assimilate the good quality data, then usually you improve your estimation, right? So could you briefly explain why, I mean, on top of plant height and LAI, adding soil moisture, you get the so the black and the red slide, the slide 11. Slide 11, number 11, I think. Yeah.
11.
Yeah, this one. So the last group is plant height, LAI, and the soil moisture, right?
Yeah.
The
you mean this one?
Yeah.
This one I think because this is it's a coefficient correlation R square. So when we add in the soil moisture into the group, we found that maybe the R square may be a little deteriorate, but the RMC index becomes better. Yeah.
But let us the statistic perspective. But I guess this could be linked to the model itself in terms of how the crop growth closely linked to soil water flow and things like that. Well, we can have a chat later on to see how to improve that part. Okay. If no further questions, then we move to next presentation. Maybe we can start with George, considering you are already here. George, are you able to share your screen?
Yes, yes, of course. Just a second. I close my camera, to save on a bandwidth here.
Okay. Yes.
Okay, can you see my screen?
Yes, very well.
Okay, excellent. Okay, so good afternoon, everyone. I'm going to present today some of the key findings that come out from virtual mobility that I implemented recently, focusing on the retrievals of soil water content and evaporative fraction using UAV data that were acquired from the field campaign that was conducted in 2019 in Palermo. This work was done jointly with colleagues from the University of Palermo and also with Salvatore. Let me start very quickly also with the presentation. Main content. Okay, first of all, about the background information about the importance of surface soil moisture and evaporative fraction. Accurate estimation of both the spatial and temporal variability of those parameters. It is something that cannot really be overstated, exactly because of the importance of those parameters in a range of fields, including hydrology and agriculture, for example, in plant irrigation, estimating plant irrigation needs, in vegetation stress, early warning, in yield production, also in other environmental applications, including fire risk, desertification mapping, or also in meteorology, and studies that are linked to the carbon and the water cycles. So we need those. We need information on those parameters on the spatiotemporal variability at different scales of observation for a large number of applications. However, it's not a really easy task. It's not an easy job, and this is because of the strong spatiotemporal variability of those parameters. Okay, that and the spatiotemporal variability of those and the parameters that are needed for their accurate estimation, which makes estimating those parameters difficult. The remote sensing observation provides a very promising avenue towards this direction, towards estimating those parameters at different scales, geographical scales. There are lots of different methods that have been developed that are proposed in the literature. Those methods vary from empirical to more physically based approaches. Already, one of our colleagues previously presented a group of techniques based on machine learning. Between the approaches that have been proposed, there is a specific group of approaches that have shown a promising potential, and those are based on the relationships that are embedded in a scatter plot that has been produced from surface temperature and the vegetation index that has been derived from Earth observation data sets. What I wanted to say here is also that those methods are really promising. Between the main reasons, why those methods are happen to be promising is the fact that many of those techniques require a very small number, a few number of easily measured parameters. They also have an enhanced ability, some of those techniques, to deal with the surface heterogeneity, and some of those techniques also provide an easier transformation between instantaneous and daytime average fluxes. So there is a lot of work that has been done that's documented in the literature around the existence of the relationships that that exist between the TS and the vegetation index when those are plotted in the scatter plot, where you can see here some of the key parameters that are involved in relation also to this presentation. The factors that affect this triangular or trapezoidal shape that emerges have also well been studied and documented. And between the different methods that have been proposed, there are different methods of different level of complexity, and some of those methods include, in fact, the use of land surface process models, which are linked in different ways to this domain, this TSVI domain. One such method is the so-called analytical triangle method, which is implemented using a soil vegetation atmosphere transfer model. This is a 1D vertical model. And this technique has been extensively evaluated so far using different types of satellite data mainly. There are a couple of studies that have also implemented this specific technique with airborne imagery, airborne data. A variant of this technique of the analytical triangle that is named the simplified triangle was recently proposed, and this technique allows basically deriving surface moisture and evaporative fraction EF without the use of the SVAT model. Okay, and this method was proposed in 2019. It was validated in 2020 and 2021. Recently, was validated also with Sentinel-3 imagery at various European ecosystems for 2 or 3 consecutive years, if I remember correctly. And also as part of the Harmonious project, the simplified method, the simplified triangle, was validated using UAV data that were acquired from the actions campaign that took place, as I mentioned earlier, in the Mediterranean side in Italy specifically. So those are those are examples of two papers that I actually mentioned. On the left, you can see the paper that has evaluated the analytical triangle method using satellite data. And on the right, you can see the work that the published paper that was produced in 2021, which consisted, in fact, the first verification study of the simplified triangle method using UAV data in this Italian site. And this work resulted as also in part from an STSM that was conducted by myself visiting our colleagues at Palermo University in 2020. So the present study builds on the previous work we have conducted altogether, and has actually 3 key objectives. The first one is to perform an initial evaluation of the analytical triangle method this time, okay, at the same setting, a typical Mediterranean setting. Also aims to evaluate, to examine the agreement in soil moisture retrievals from this technique, from the analytical technique, at different soil moisture depths for which we had available ground measurements. And the third step was to actually focus on the simplified triangle and evaluate the special aggregation effect to the SSM retrievals by this technique of using exactly the same ground data as reference data. And this work was completed only recently, as I mentioned earlier, as part of a virtual mobility that took place in February. A little bit of, very quickly, just to mention some information about the experimental site. This is located in Palermo, very close in Palermo, in Italy. It's a citrus orchard field. The area is a typical Eastern Mediterranean semi-arid environment. It contains tangerine trees, about 400 plants. Plant density is about 400 plants per hectare, and it is irrigated. The study area also has a flat topography. The elevation varies from 30 to 35 meters, so it's really very small variability in terms of topography. And also the slopes vary between 1 to 4 degrees, 1 to 5 degrees. An interesting aspect about this site is that's worth mentioning is the fact that it is implemented different irrigation. They implemented 2 different irrigation schemes in the field. Okay, one is a full irrigation scheme, that is in that area between ST1 and ST4, and stations ST1 and ST4. And the other one, and the second one is under deficit irrigation. Those numbers ST represent the locations for which we have installed the instrumentation for measuring the soil moisture, and ST9 is the location on which an eddy covariance system has been installed and acquires data. In terms of the data set that were used, the fieldwork in this case, in this area, was carried out in July 2019. A series of data, especially UAV images and other ancillary data, was acquired on several days during the duration of the campaign. And in this specific study, it has been used only one imagery, one data set, one UAV image that was acquired on July 30th. So we had available multispectral imageries, 3 centimeters, and also thermal images were also acquired at 3.5 centimeters. And all those data was available concurrently with the ground observations of the site. To implement the technique, some pre-processing needed to be carried out. We included basically some standard pre-processing steps, like the resampling of the data, all the data to 4 centimeters resolution, an orthotification, a calibration of the optical data to reflectance, and also a calibration of the thermal infrared data to radiometric temperature. And you can see here the final images after the completion of the pre-processing. Those images consisted, in fact, the main input to the techniques implementation, together with the ancillary data / ground measurements that were available at the site. Okay, that were the requirement for that was different and dependent on the technique, obviously. So after completing the processing, the pre-processing of the data, the first step was to implement the analytical triangle, as this was linked to the first 2 objectives of the study. This analytical triangle, for those of you who are not familiar, what it does is basically in the technique implementation, we have the TSVI domain that is coupled to a SVAT model, the SimSphere SVAT model in this case, that is being parameterized for the test site conditions. And this coupling allows deriving a set of second or third order inversion equations that link the triangular domain or trapezoidal domain to the soil moisture availability and the fluxes, the instantaneous and instantaneous latent and sensible heat fluxes, but also the daytime average ones as expressed by the ratio to Rn, net radiation. So those second order polynomials or second or third order polynomials take, have this shown this format. So we have this flowchart shows basically the technique implementation, the main steps of the technique implementation. So this procedure was followed to retrieve soil moisture availability at the site and also the latent and sensible heat fluxes, both instantaneous and the daily average ones. And the results specifically of the soil moisture were compared at different depths for which we have available the different depths, and also at different times, because the acquisition time of the satellite data of the UAV data was at noon or at around noon. Moving on to the next, just the next technique, the simplified triangle. It's in a little bit different way. More details on the technique are provided in also in the papers that I have also referred to earlier. So given that I have very little time, I will not go into very much detail. But what we need, basically, this technique, what I would like to say is that this technique allows deriving estimates of surface wetness, the soil moisture availability, which refers to the first few millimeters of the surface covered by the bare soil, and also of evaporative fraction. Okay, and the principle on which this method is based is illustrated here on the figure on our right-hand side. Briefly, this technique, the key inputs that it requires include the fractional vegetation cover that is derived from the NDVI, and also the surface temperature. Okay, we basically, what we do is we implement this technique. Here you can see the way the soil moisture soil moisture availability is retrieved from the temperature data, and then how the EF is linked to that. And then the next step was to convert the soil moisture availability to soil moisture estimate using the field capacity value, an average field capacity value that was used in the field. So you can see here you can see here basically first of all the scatter plot of the FR and T star. T star is the scale temperature. It has to be scaled to vary between 0 to 1, and you can also see the maps that were produced on the left. Here is the surface temperature, the scaled temperature, and also on this one here is the fractional vegetation cover. And the comparison of the soil moisture retrieval was done at different spatial resolutions at 0, 15, 45, 135 meters, 4, and 10 meters. In this case, in this scenario. And this relates to the third objective of the study. Okay, so to move very quickly to show you some of the study results. First of all, concerning the first 2 points, 2 objectives of the study. Here you can see the derived maps of SSM, LE, and the H fluxes from the analytical triangle technique implementation, including also the corresponding histogram in this case. And the first step of the analysis included a visual comparison, basically inspection of the spatial variability of the derived parameters. And as you can observe, both the evaporative and the soil moisture maps, you can see here actually the evaporative maps, the EF, LE, and H to Rn, the daily average fluxes. And you can see basically that there are reasonable values and ranges of values that have been derived for the different parameters, which seem to be in accordance with the spatial variability of the vegetation and the soil components in the partitioning on the ground. After this step, and continuing on the visual inspection on the results, and to further illustrate the above observation, we investigated the variability of the derived parameters separately, the partially or fully vegetated components, and you can see the results here for the vegetation, the vegetated component only of the experimental site. And this, the separation between the vegetated and the soil component was done using a masking method, using the NDVI thresholding. And you can see here also the, as I mentioned, the vegetated components and the variability of the parameters in the vegetated component. Well, similarly, for the bare soil component, you can see the results here. And also the corresponding histograms in its case. I have also included here the summarized statistical results that concern the comparisons of the soil moisture available, soil moisture content, surface soil moisture content that has been derived from the analytical method. P represents P 10 centimeters is the depth at 10 centimeters. Similarly, is at 20 centimeters, 30, 40, 50, and 60 centimeters. And the statistical methods that were used to evaluate the agreement were initially those three that I have included here, the bias scatter from which the RMSE was computed. And what we can see here is basically that, first of all, we can see that RMSE seems to be generally satisfactory. Ranging, and also we have the different times. I forgot to mention that. Sorry. The different times. Here is the key time. Here is the time closest to the UAV data acquisition. But we also perform the comparison using the ground data that we had available 1 hour before and 1 hour after. So you can generally see, that the RMSE is satisfactory, ranging, from 0.096 to 0.03. The best agreement, obviously, and as would be expected, obtained in the top surface layer with an RMSE of 0.096. The results generally suggest that the technique was able to predict satisfactorily this parameter, especially obviously as expected at the surface layer, at accuracy level also close to those that are reported in other studies that having the same technique but using satellite data in different ecosystems or similar ecosystems. For the EF, it was not possible to conduct comparisons, statistical comparisons, because we had only one allocation available, but we plan also to perform some comparisons of the flux footprint that we have. And then we move on. Here you can see the results, the scatter plots. Actually, we move on now to the third objective of the study. You can see the results of the third objective. And you can observe the scatter plots that have been produced at the different spatial resolutions that were implemented using the simplified triangle method, okay, this time. And you can observe this shape, this triangular or trapezoidal shape, gradually disappears as the spatial resolution decreases, which is of course something that someone would expect to see. However, this is something that creates practical difficulties in terms of the method implementation for finding the cold and warm edges. And let's see now also some.
Sorry, do you have?
Okay, close very quickly now the presentation, so you can see here simplified results for the different scenarios, and here are the statistical comparisons also for the different scenarios at the different depths, so most of depths, and at different times. I would like to, I'd like to say a bit more, but perhaps there's more time. And to close, some important conclusions is that this study consists of the first verification of the analytical triangle using UAV data. Is of course implemented with one imagery only, so it's an initial investigation. The results are promising and comparable to other methods. There are some limitations that if someone is interested in applying those techniques should have in mind. For example, you know that the heterogeneity that is required in the launcher phase. The technique has some advantages in comparison to other similar methods. And specifically for the implementation of those methods with the UAV images, I have here summarized some of the advantages of those methods. And what I would like to say closing is that, of course, those results that I that I share with you now are based on single image analysis only, and are based on one specific case study, and of course can be interpreted only in the context of an initial investigation and exploration of the techniques, implementation and validation, and further work can be done towards verifying the applicability of the methods in different or similar environments in the future. That's very nice. Thank you.
Okay, thanks a lot, George. So I think we don't have enough time for questions, but then I understand that you have you can share with us this presentation, right? And later on, people can look into the papers and maybe send the. Yeah.
No problem.
Okay. Great. Thanks a lot. So Salvatore, you want to talk about future opportunities? Would you like to take over the floor?
Yeah, no, sorry, George, if I interrupted you, but the topic is, I mean, all arguments are all of great interest, and I think that we are familiar with most of them. Some probably just I don't know. There is someone trying to enter. So the main issue and the main element that it might be nice to discuss with this group, and considering the fact that the group has been productive since now, obtaining different success in terms of funding, because I remember we applied for an Horizon 20 that was migration, that was a good idea. Migration climax, if I remember well. The AI aqueduct that was funded, and it's something that is still running. We have the cooperative funding between Federico II and Tel Aviv University, which is also one of the motivation for the activity on Seile River. So this is a totally success story for Harmonious. So the question is, and the things that have been discussed in other working groups are the achievements, and here we have a lot that has been achieved in terms of research questions that have been addressed. Now, the main question that I would like to pose, and I would like to stimulate, I probably will use part of the coffee break to talk about this, is not much, because the schedule is tight. So, but The question is, what is the next hot topic for the soil monitoring that could be tackled? And I see there is already good research questions that are on the table. The question is, can we identify the most intriguing one for a European call? And in this we have options. So since in the management committee tomorrow we will talk about options and try to identify correspondences between proposals and opportunities, let's talk about research questions first.
Yeah, thanks a lot, Salvatore, to bring this up on the table for discussion. I think, I mean, like I mentioned yesterday during the summary for Working Group 3, although the soil moisture, for example, when we talk about it, it seems kind of isolated variable. But yeah, the soil moisture itself, of course, is connected to many processes. So like George presented, it's also linked very closely to surface temperature and evaporation fraction. So in that sense, I think it is not only about soil moisture, right? When you are talking about the
not necessarily. The question, the motivation for this is the following: we are closing the action in mid of April next month. No?
Yeah.
And after this event, it is very unlikely we might have the chance to have an additional meeting with Harmonics with funding. So, of course, we have other fundings which are fine and can allow some of us to interact in the future. But it would be good to have a new frame or new funding frame for the next future that is, of course, is functional to research activities that are of interest for a bigger community like the Harmonics community. So the motivation of my question is try to identify the right topic that is able to aggregate a fair amount of scientists that are sitting at this table and on the other tables that may be interested in approaching in the coming future similar challenges or similar interaction like the one we did since now.
Yeah.
So in this regard, I will try to make a short sort of interview about what do you think it might be a nice research activity or research question in the next future. It means from now, since 4 years from now, no?
Yeah. Are there any?
Giuseppe, well, it's a great idea.
No, not good idea. Just some brainstorming. I think we can focus on organic content. Okay.
Yeah.
Also nutrients that are inside the soil. This is the challenge. The moisture now. Okay, we have a lot of paths, a lot of methods, so we can continue to go in deep.
Soil fertility.
Yeah. But I think also Brigitta can give.
Yeah.
Yeah, Nunzio mentioned the water for all call, so it would be good if all of us checks from time to time what fields or what topics are written, how we could match what we have in mind.
Yeah.
It's not the only option. Water for all, it's an option, but let's think about the research topic first.
What about machine learning and deep learning, for example?
Yes, this is one of the trending.
I had no doubt that was your suggestion.
Yeah. So maybe I can try to add something here.
Good topic, but it's a technique. So
Yeah.
what about the scientific question?
So I think what Giuseppe mentioned, the organic content is definitely, well, we can say not necessarily focal point, but could be the starting point. If we look at the FAO, let's say current hot activities, the soil organic content mapping is one of them. So it is encouraging all the countries to report their soil organic carbon stock. And I believe AR and Nicholas are also involved in one of the European Space Agency projects in terms of utilizing remote sensing techniques for mapping soil organic content. In less times, I think with UAV to map soil organic content is under developing, I would say, in that project. But this is just on the topic, right? So the science questions behind, I would say, okay, how the soil, water, plant, atmosphere, and energy interaction will impact all of this. So how to understand the change of soil organic content or soil carbon stock, and heat water flux. So I would say we take the agricultural or natural ecosystem as one continuum, and then trying to see what the techniques, for example, machine learning, UAV, satellite, and all kind of also eco-hydrological model or soil model can combine to understand the change. And all this, I think, will very naturally to sustainable development goal like SDG. So it requires more than 15 minutes discussion, I believe. And now we already need to move to the next one. But
we have time tomorrow, because I think that this will be we will dedicate a part of the MC meeting to this brainstorming. But
okay.
For me, it's good now to collect suggestions, ideas that we can put on the table tomorrow.
Yeah. And the soil property part, I mean, as Brigitte is doing, is also very important. So I think most of the topics or working groups in Aqueduct can be also contributing to this part of the discussion. Either it's water for all or other cause. Yeah.
Yeah. One small comment that machine learning is a technique, but you can also research on proposing new architectures that improve over what we have now. Because right now we focused the first part on applying something to our problem, but we can also research on proposing new architectures that improve. That's my field. I am researching on that. So this is only the beginning that we are applying now. So it's a great line that if we can follow with that.
Yeah, thanks a lot, Ionut. I think that's also a good point. I think there are two parts. One is the purely focus on remote sensing, purely focus on machine learning or deep learning methodology or algorithm development. But there's also another very hot topic lately, which is integrate the physical process with the machine. Yeah. So it's kind of physics-aware machine learning type of study, and this is very much linked to destination Earth or digital twin Earth as pushing very hardly by European Union. ECMWF is behind it, and it's a very big project. Yeah. I guess Salvatore and Lazzaro, for working group 3, I think time is up.
Yeah, it's up. I don't know if there are other. I mean, I collected 2 suggestions, which are fine. Of course, I understand the interest in machine learning techniques, which is a tool that we deeply exploit in the working group 3. No, and the presentation have been a clear example of that. Artificial intelligence, machine learning is now a keyword that is almost in all the calls of Horizon. So I suspect that no matter what is the idea that we develop, it's a tool that we will exploit and apply.
Yeah.
The idea of monitoring, monitoring organic contact, soil fertility, and impact of climate change. I introduced this new element just on soil evolution. It may be a key issue, no? May be really intriguing. So this may work. Okay. So this might be an option to put on. Regarding the calls, we will see. There are options. We'll try to discuss about this tomorrow. Okay.
Okay.
So guys, thank you so much.
Thanks a lot. Is a working group for meeting is also in this link, right?
No, I missed this part. What did you say?
We continue stay in this room for if you want to join.
If you want to say to the next working group meeting, yes, the room is the same. We will just interrupt to have a pause of like 20 minutes from now, and we will restart at 4 p.m. Okay.
Then before we leave, maybe I have a question for George. George, are you still there?
Yeah.
So I think is George still there? Is muted or no?
George?
Oh, okay.
Yeah. I don't know how many Georges are here, but I am one of them for sure.
Okay. For your work presentation, for the simplified triangle approach, I understand you need to use the average field capacity, right?
Correct. Yes.
And later one you get it from the field.
The average field capacity.
Yeah.
Yes, that was measured from time to time in the field, as far as I know. Yes, I got this information from who is managing all the sites, all the instrumentation installed in the site.
Okay. So in that sense, maybe what the Brigitta is trying to push for the spectral transfer function, for example, can be applied here. Using the UAV data line. Yeah.
Okay.
Okay. That's all. Sorry.
Yes, we can talk if you want about that with.
Yeah, sure. We can have a meeting maybe later on together.
Of course. I'll send you a presentation as well. Also, if you want, you can share it with the
Sure. Okay.
Thank you very much for the opportunity. And
thank you very much.
Nice afternoon to everyone there.
Okay, then see you guys.
Okay, thank you so much. Bye-bye.
Ciao, Giuseppe.